1, 2, 3, 4, 5. Okay, so finally I can continue streaming. I was very distracted on Instagram because there are a lot of proposals how to improve Instagram. Really a lot of them. And also when you try to use ChatGPT, then it gives you a lot of information. And also this part that I'm going to discuss right now, it's rather not easy part, and I need more preparation for it. So we'll start approximately now, but in a second. Okay, my app wasn't loading as quickly as I liked it to be loaded, but it finally works. And okay, let's just jump to the chapter 4, where we where we stopped. And okay, actually we don't need chapter 4, we need the second part of chapter 4. So today we will learn deep ideas about the tight binding model. And I actually became more productive in my workflow. I understood it's important to speak with AI chat before doing yeah, okay, let's be here. Before doing the stream, I have just updated this file somewhere, but not here. And let's open right now also some plots that will be the K plots during the stream. You can remember these plots from the previous stream, from this article that was from the last stream, and announcement that today we will discuss what tight binding modeling can give us. And maybe I can share some valuable insights which I learned after reading and discussing with ChatGPT. But general preface is that this part of article is not an easy one. Of course, it does not explain many things, but the ideas which are there, these are not easy ideas. However, if you think about them for several days, then they become not so complicated, but still like derivations that are cited here. These are very hard derivations. I can just tell you what's done here and what I understand about it, but reproduction of these results is work for at least several weeks. If you know basics of condensed matter. Okay, let's continue with the place on which we stopped last time. So here they say Slater-Koster tight binding model. That's the model that they are going to use. So the first question that I was trying to answer for some time, and I forgot to turn off notifications also. So the first question is that like we were given the Perles model, and now we are dealing with tight binding model. So there is a question between connections of them, and let's double check that I have worked this question out, because I was thinking about it and I wrote something, but I'll post myself a reminder to double check. Okay, so my answer on this question is the answer that I learned from ChatGPT. So that's the best thing I can answer on this question. And the answer is that like we are trying to do different things in the chapter 2 and chapter 4 here. In chapter 2, there was main goal was to derive the phase transition and this distortion, and also to predict the like distorted like how unit cell changes. So we work in the K space, and then the period doubles for the one-dimensional model. For two-dimensional models, there are some comments, but nothing is really clear about it, at least from the chapter 3, or maybe chapter 2, because chapter 2, I think that's the chapter where there was a paragraph about dimensionality and also weak and strong coupling. So for that model, the goal was to derive the phase transition. That model was assuming some physics of microscopic interactions between particles. And the same microscopic interactions can be used for description of bands in the crystal. And that's how we can get the tight binding model. So I guess that the origin is the same, but somehow we can derive that model of susceptibility and what is also in scope of that model. Okay, actually, I can just easily do like this and see my collection of main formulas. So always around susceptibility, basically. Normalization of frequencies is a function of susceptibility. And basically that's the main formula. There were, of course, many other formulas. And there is this still important question: how does this change of the phonon spectra influences electron bands? And we remember from the previous talk that there was a plot that answers this question. And where is that plot that I imagine? Okay, maybe that's this one. I'm just confused very much. I thought it's somewhere here that we were saying that for tantalum deselenide. But I don't know. It should be somewhere. Okay, I don't know. Maybe I confused a lot of things already. Okay, but I scrolled through article, don't see any better plot, so let's just stick to that one. Maybe that was the proper part. But that's very strange, actually. Okay, let me just check the images which I have for this plot, for this article, I mean. Where is 01, typical theory, and now on the origin of this thing. And I meant actually this part. So, I remember that was the part of excitonic insulators, and I didn't open this part during my scrolling. So we were told that excitonic insulator model is applicable for tantalum deselenide, and that was the electronic band, that was the phonon band, and it softens. Now we see again actually a question which I didn't write, but why in figure 7c? Yeah, okay. That's what I didn't point much attention to, but okay. What I wanted to say that basically in this model we have this prediction, the change of phonon frequency, which you have just seen on that picture, and also the change of electronic spectra, but we were not given theory about it, and that's why it's better not to comment, because I have no idea how this interaction of bands can lead to lowering energy of the band. Maybe it even goes way beyond of this model that is presented in the section 2. Okay, so that was this model before. Right now the question is that why do we have a tight binding model? And I'm trying to answer this question. So my version is that the microscopic interaction can be analyzed from the point of view of phase transition or change of phonon frequency. And if we go to this path, then all this picture of parallel instability, if you carefully generalize it for two-dimensional model and for strong coupling, should be used. And if it's used, then you can get the instability. But if you want to look at the band structure of electrons, then always we assume that there is a tight binding model. It's also, okay, yes, I don't know why exactly the tight binding model, but that's a standard approach. And definitely, maybe ChatGPT even will answer well about it. But there is the standard approach which deals with electron bands. It's called the tight binding approach. And that is always assumed in normal state and in the state of charge density wave. The only thing is that the bands are changed, and this will be one of the biggest part of today's stream, to understand how they are changed. Okay, we have really important citations without which it's impossible to understand which model they work with, but okay, later I will read it. And I don't know what is Slater-Koster tight binding model. I haven't asked ChatGPT about it, but okay, I mean, there could be tens or hundreds of questions about this tight binding model, and this discussion goes beyond this article. So some special tight binding model. Why exactly Slater-Koster? It's also unclear. Maybe because clever people know how to extract some parameters in this model from some microscopic models, and maybe they work, and maybe they are the only ones that work. That's just my guesses. Okay. And okay, this model has some parameters which are known for me, but then it's written that they extract them using first principles band structure calculations. And at this point, I don't understand it, because like one way which we can go is to extract them from experiment. Another way is that from some calculation. And maybe that calculation that's my interpretation why they Rossnagel writes like this, because that cited band structure calculation is complicated, so it uses numerics, and most likely we can't. But the binding model also uses numerics. But maybe it's way simpler, so that's why we do approximation of this first principle band structure calculations. However, it's very interesting for me to learn what does it mean, this work about first principle calculations. Okay, that's how it's written that we get the parameters. And that's very important actually to know the parameters, but here we are given only citations and results. We are not given the parameters, and we're not discussing them. Okay. Now, okay, we have again the statements about the bands and orbitals, and I can't comment much. This generally this part requires a good preparation in basics of solid state physics, where there is a discussion of this typical effect that if you have two orbitals, then if they come together, they can overlap, and this overlap corresponds to a band. And here there is the statement which exactly orbitals overlap. Unfortunately, I can't tell you much about it because I wasn't thinking about orbitals of atoms. And also, of course, I wasn't deriving band from overlap of two orbitals. We need maybe to evaluate some like overlap integral, and then based on this exchange interaction get some parameter, but that's not the thing I can reproduce. So the only thing that we're given here is the answer that exactly these bands interact, overlap, I mean. That's for the second material, actually. That's for the third material, and that's for the first material. And I also can't comment you why the DD interactions, it's just known from some cited paper. And also, like in tight body model, there is an interaction between several, neighbors. That also, like, if we neglect the next near neighbor interaction and second neighbor interactions, then we have less parameters. And okay, it's absolutely clear for me why, but for some reason in this material, the tantalum diselenide, second one out of 3, we have we have also second neighbor interactions. So anyway, we will be presented with results, and this just the comment about the tight binding model is assumed for these results. So I can't explain also like why exactly such neighbor interactions are there. Okay, and the third material also only these interactions are considered. These are again comments about tight binding models which we haven't seen and which we will not see in this article, but we know what is the name of this tight binding model. That's about just these citations. So Rossnagel decided to add some comments instead of writing nothing. Another thing is that for tight binding models, there is spin orbit coupling and intraatomic matrices, some intraatomic matrices. So what is a spin orbit coupling? That's what I approximately can imagine, because on each orbital there is a spin of electron, and there is this like I just forgot, it was so long ago, like in typical quantum mechanics we have, I think it's about the energy splitting, that different energies with different spins, if you look very, very close to it, they have the splitting which can be calculated using some relativistic quantum mechanics. So in general, if we have like different orbitals, then they can interact, and advanced version of tight binding model should take into account this. Let's approximately understand, but what are intraatomic matrices is the thing that I have no idea absolutely, but that's some generalization of typical tight binding model. And there is a Hermann-Skillman value of spin order parameter. That is absolutely not clear. We can only read these cited papers to understand what is it. So that's like a thing that adds to the tight binding model that was announced to be used. And the outcome is that this is the dimensionality of the Hamiltonians, 10, 20, and 9. Again, that just refers us to the cited papers. That's not the statement that we can understand without looking to these papers. Now there is an introduction to the plots that we are going to discuss during this stream most of the time. Plots 8, 9, and 10. So 9 and 10 is the similar plot like this one, but for other two materials. So we will see them in the future. And there is little contradiction because before it was written that we're taking parameters from the first principle calculations. Now it's written that we're taking parameters from fitting. Maybe we're fitting to the first principle calculations. And here we should assume it is calculated already band and not experimentally measured and fitted to experimental. That's how I understand it, that we just fit to already some theoretical calculations. And I still don't understand why we need to fit it at all, because first principle calculation works, so we can maybe work still with them. Another possible answer is that here we're dealing with charge density wave, and to explain the band structure in charge density wave, we need to use some advanced theory, so first principle calculations will not work already. And to do this, we will do several steps that I'm going to discuss during this stream. And the outcome is that this plot that is calculated is some kind of similar to the plot that is experimentally measured. You will see also similar plots like this during the stream. And just reminding you that this was the thing that we discussed before. And here is the new plot, and below there will be some new plots. And also in this reciprocal space, which we always work with in this article, we are restricting us to these planes. I unfortunately can't comment you about the the reason of this restriction. So you can see like gamma mk is the flat plane, and a l h, it's also a flat plane, but it's at the top of the this object of the Brilliant zone. 1, 2, 3, 4, 5, 6 hexagonal Brilliant zone. But like as I said before in the previous stream, I am not expert in these directions. That's what used throughout this article, and I haven't reached discussion with some AI or some basic books to understand this geometry. So, but that's what we are given in this geometry. There will be all of this modeling. Okay, here is the image, and we're going to return to this image several times, but it will be here at the left as the one extracted from the main text, to this special section where I extract K formulas. So that's a reconstructed band structure. So it means that we have, I guess we don't take into account temperature at all here. So it's like, what if we had no distortion of lattice, but just electrons there in this configuration of undistorted lattice. And that's what I imagine. Now there is the theory that we will discuss later, the unclump scattering. And the idea is that it's very hard to explain this idea, but suddenly we have a lot of bands because of the Brillouin zone shrinks. So the basic idea behind all of this part is that since we know that period doubles in the one-dimensional case, then we can guess that period approximately doubles or some kind of increases, and that's why Brillouin zone is some kind of decreases. And maybe it decreases 3 times based on this picture, for example. This little Brillouin zone is 1/3 of the big Brillouin zone. But but this shrinking makes the bands make the bands overlap, because bands still the same remain the same. It's just the Brillouin zone decreases. And I haven't actually learned this connection between this Fermi surface and the band structure. It's not very obvious for me, but somehow that should work here, that if we look at this image, these are the Brillouin zone, so each line is a band. I mean, it's what is left from the Fermi surface, but if we look not on Fermi surface but on the bands, there will be also some lines of the equal energy. And okay, I mean that I guess that if we fix energy, then all the bands will be somewhere here in this picture of the Brillouin zone, because as you see, this is the direction the same as here. So we go along this direction, then along this direction. So gamma m, let's see. So yeah, so maybe that's how it works, since we have, okay, I don't know how it works, but there should be some connection. And okay, you need to read some cited literature or discuss it with a specialist, or read again for 15 hours basics of solid state to understand this connection. That's already a good motivation to do it. And somehow, because of this shrinking of the Brillouin zone, we have these extra bands, and they're called unclap bands because that's a similar effect for the electrons in metal, where there is this scattering which contributes to thermal conductivity, as far as I remember, and they're called unclap bands. But now there is the gap that appears between them. Why the gap appears between them? Because, let's look at the caption. Because we not only have the shrinking of the Brillouin zone, but also change of the atom's atomic lattice. And if we add the change of atomic lattice somehow in the tight-bodied model, then we will get these gaps. And it's called bond straightening. And what is bond straightening? Maybe it's the consequences of the fact that atoms move together, so hopping of electrons was maybe increased. That's why kinetic energy became more than potential. I mean, no, vice versa. Potential energy became more than kinetic energy, and that's why there's this insulating effects appear, because I'm not expert, but I think based on other articles that that's the insulating state, and that's the insulated state. Maybe actually we can just look at the gap and say, hey, there is a gap, and obviously it's insulating state. But I remember that plot of resistivity, which clearly says that the commensurate density wave is insulating state. Yes, I'm pretty assured based on the literature that I have read. And okay, we will discuss this plot later. Here we are presented with spectral weight, and the big part of today's stream is the discussion of spectral weight also. I mean, nothing is explained, but we have a lot of statements about it, so we will look at this plot later. The spectral weight is an important concept to understand in order to understand this article. And as far as understand spectral weight is the probability of electron to be at some position in the band. So maybe it means that spectral weight is temperature dependent, but okay, let's just check it. Okay, I'll look at it later. Let's forget about the temperature. So right now there is this probability of electrons to be at some energy that's related to the bands, and that was calculated. That's distribution of electron probability. And we have some gap here, which we'll discuss later. And we can compare the distribution of electrons without the charge density wave state and with charge density wave state. And B, let's double check. Yeah, so that's already half of the transition to charge density wave, because it doesn't take into account lattice distortion. That's the full transition to charge density wave, and later we'll compare it. Okay, maybe we'll not compare it. Maybe I'm just wondering that. So that's plot. This plot looks exactly like this plot, right? But this thing is different. If we forget this line, okay, it's a good question, which we'll think later. Okay, that wasn't the thing that I thought about, but they should be the same. We see that to some extent they are the same, except that this point is here. We have these three lines, but here I don't see that they're very the same, so I'm not very sure. But okay, that's what happens on this image, and that's the result of tight binding model. We don't have much comments about it, and of course we don't know parameters in scope of this article, but we have cited papers where there should be some parameters, all of the parameters, I guess. And actually, next article will be also about this material and how it can be modulated with different parameters, but that's not the one that is cited in this paper. It's actually a really good idea to read these papers to see how they did the calculation of this. Okay, here it's written that some effects will be simulated, and I guess it means that it's a charge density wave and the periodic lattice distortion. Yeah, so here is the first step to fit something, maybe first principle calculations, and that was the fitting. And okay, that's not very clear what is this, because here we don't have this, but no one is interested to discuss this. And actually, yeah, it's like 7A and 8A. Why are they different? It's a good question. Okay. I don't know why these plots are different. Never thought about it, but only now I noticed that here we have this dynamics of, change of a band, but here we don't have this change of a band. Not okay. Yeah, that's what we're going to do, to do this from this. Let's just open this figure, which is meant here. Okay, here I don't know what is really meant, that Hamiltonians are opened out. But idea is that before we had this big Brillouin zone, after we have this little Brillouin zone. So it's not clear what is meant by opened out, but I guess that's what meant. And there are statements of dimensions. Here we have reduced Hamiltonian of dimension 10, 20, and 9. Here we have dimensions such big that no one will ever write them on a paper. So okay, no, I can't explain what's going on here in this sentence. We are given again a comment about model which we'll never see in this article. Now we are moving from this big Brillouin zone to a little Brillouin zone, and it's written that these Hopper integrals that are assumed in tight body models, for all of the materials that we deal with, they are scaled like this. Does it tell us something useful? Well, maybe if we do like really detailed calculation, it will give us great insights, but right now we know that these parameters should change, but how exactly, it's something that is very far from current our understanding based on this article. So these integrals change, and hopping parameters, hopping integrals. So somehow they calculate these parameters, and if we know how Brillouin zone is changed, how atoms are, yeah. Okay, maybe we are told about the total, like two effects when atoms are moved and electrons are moved. And if atoms are moved, then these integrals are changed according to this law. So it might give us a hint how the parameter is changed, and if we know how parameter is changed, then we can show how the band is changed. That's the idea. I'm just wondering if there is internet, but I hope that there is an internet. At least I have a signal here that shows always green, so it should be an internet. Okay. Yeah, that's what's written here, that bonds are changed because of this change of atoms. But of course, again, we need to calculate it somehow, and that's really impossible to do this calculation. So there was a discussion of this change of parameters. These changes, and yeah, so it's not clear from which experiment, but that's the question for the previous part, for previous stream, where in this section 4, but before this text, there was a discussion of the change of positions. And I don't know how it can be done experimentally by maybe some very precise measurements. And it's written here that that's enough to predict how electronic spectrum is changed. But also they neglect some of these movements, like non-radial atomic movements and reconstruction in that direction. So I have no idea how to take into account it, and also have actually measurements in the Z orthogonal direction. But for some reason they neglect it, maybe because there is a big sense in doing this. Nothing is commented much about it, how reasonable is to neglect it. Okay, now there is next paragraph, which is very important. So it's about the spectral weight that we are calculating, and I will erase this question later. I will add the answer that that's what we see from ARPES. So ARPES is the shining of photons, and then it measures which electron go out. I don't know really how it works in detail, that we can have this plot as a function of like Brillouin zones of momentum, but okay. Somehow we have this plot and this intensity of photons that are emitted, or no, maybe electrons that are emitted. So it's proportional to the spectral weight, and that's why we need to know how to calculate it, and here is the main part about it. Okay, it's said that the spectral function approach is working. But now too many bands, because okay, it's not shown here. That's the picture, so we have actually a lot of bands. And what is this spectral function approach? I guess it's the same as for the Green's function approach. I'm just double checking the internet, because is it working or not? Okay. Yeah, because I have a chat on my another phone, and another phone was telling me that there is no internet. But that's not a problem of internet, that's a problem of the phone. And I think I have fixed it. So the spectral function approach is thing that I think is just in scope of the Green's function method. So we're not told much in scope of this article what this approach is, but we have the cited papers to understand. But some spectral function approach will be used, and that's the spectral function, and it's also manifests itself in the experiment. That's the main idea. Yeah, and that's the very important question, which I, of course, can't answer, but later I will approach it. So, like, if we speak about this material, is it really important to consider several bands, or we need to consider only one band? Because in the previous streams, nothing was written about different bands. And that makes me think about, is it really possible to apply model with different bands? I mean, is it about models with one band? Maybe model with one band is not applicable at all, because here we clearly see that there should be several bands to explain even the spectrum of the shear density wave state. Okay, but let's look at this approach that is proposed to calculate a very important parameter of the band structure. Okay, so the idea is that we, like after we have the shrinking of the Brillouin zone, these bands change like this, so they overlap a lot of times, one and another. And how the spectral weight will be distributed, well, that's the probability of electron to stay on some another band. That's how I understand it. So we just sum over all these probabilities. So that's like a quantum mechanics where there is the initial state, the final state, and the probability of coming from one to another. It's just the product of them, or like module of it squared. And let me not comment much because that's the standard approach of quantum mechanics. And that's the whole idea of this wave function. Yeah, it will be a big talk about it to explain what it really means, but nothing is unusual here. That's basically just projection of one state to another. And now we have the formula for the spectral weight. So it sums over all initial bands, all the final bands, and also it depends on k and omega. So k is the horizontal line, omega is the vertical line. That's what I understand. And J prime is the reconstructed eigenstate. So it means that if we shine the photon with frequency equals to exactly the reconstructed eigenstate, and maybe it means always it means always from the Fermi surface, from this line. And maybe we don't have anything here because just run no electrons higher than Fermi surface. That's my version. Yeah, and we have discussed already figure 8, figure 9 and 10 will be similar. And of course I don't understand how to really do it, but in general I understand these features of this of these figures, so we have discussed this already basically. And okay, that's the figure B. As I said, there is this shrinking of the Brillouin zone, which gives us these club bands. It doesn't really important to know what is club. It's just the term that is used from the like typical theory of electrons in solids. But the important thing is that we have a lot of these distorted bands because of distorted Brillouin zone. But again, on this point, I think it's very important to say that we already know that something happens, that the Brillouin zone somehow shrinks like this. So to know it, we need to do some measurement. So it's basically an attempt to calculate something if we already know the input. Okay, but that's a good question to write for myself, that Yeah, maybe that's the question which is unanswered, and that's maybe an important question because I had one hour discussion about this paper with one postdoc who worked with this material, but I don't remember much. Maybe that's what he said. That here to work with state body models, we need to know that Brillouin zone shrinks, but we know that Brillouin zone shrinks from experiment, and from experiment we also get the plot of the spectra. So with state body model, we are not getting any new information. We're just comparing. Okay, actually, it's interesting. Yeah, that's an important question, but I don't know the answer, because if we fit everything to experiment, then maybe all we need is to just do experiment and that's all. Don't do any complicated calculations. Of course we can do, but it requires input again from experiment. So it's just a fitting from experiment, and we maybe say that, hey, we just forget about it. Rossnagel even not writing us exactly the model that is assumed, which is also a bad sign of this theory. Okay, these are the bands. Then there are some shadow bands, right? Yeah, so this, okay, let me just show you. These bands are called shadow bands. Why they're called shadow bands, I don't know, but here in the ARPES, we don't see them. And one of the important message of this article will be that, because it will be written in the future, so it will be that here they are there, it's just ARPES doesn't see them because they have way less spectral weight than these bands, which are nearly near the initial band, this one, without without distortion. But we see that even this first principle calculation is very different compared to experiment, because here there is clearly nothing, here there is a lot of things, there are a lot of energies possible. Yeah, and here there are a lot of energies possible, here no. So that's a big question which I have already written during the stream. And that's what we have discussed. These are the shadow bands, which are called so because we don't see them much. And now it's written, I mean, I have already discussed this figure C, this one, it's written that it's because of bond strengthens and weakens. So that's another way how we can speak about it. One way is to say that gap appears because obviously it appears, but why is it so? Well, because of lattice distortion, but what lattice distortion gives us? It gives us like change of a bond. And all of this is the same, and somehow it gives us that plot, but we are not, we don't know at all how it happens. I mean, I don't know how to calculate it, that's why there is the question about it. And now we will discuss these effects in more detail. By the way, when I was calculating number of pages for today's discussion, I miscalculated and thought it was 7.5 pages, but now I'm not sure. So, okay, as usually during this stream, we have, during these streams about this article, we'll have 3 materials, and we start with this, the first one, and that's already an image that corresponds to this material. We don't know what are the parameters. That's the big weakness of this article, that it presents us the model, but we don't know even what the model is it exactly. Okay, now we know from some experiment that that's the change of the tantalum atom. I mean, some of tantalum atoms. And okay, I can open just it here. That's the figure 8. So we are always told about this figure here in this paragraph. So these are these reconstructed bonds that they are presented here. Bands, I mean, with gaps, yes. What is it? Okay, let me just do a quick pause and I will come back and we will continue very shortly. Okay, let's continue. So here it's written that what 13th electron resides in distinct band and Fermi level. So that's exactly about this band, and I was trying to understand why is it so, and unfortunately I didn't understand. But I also was trying to understand why we have the 13th exactly electron. And okay, I just maybe explain why there is the 13 electrons. So because that's David star, there are 12 electrons around it. Let's just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They're around the main 13th electron, and that's why 13th electron is selected, and it's not changed, and it resides in a distinct band of the Fermi level. But no, I don't understand this. Okay, I just understood why we have the selected 13th electron, because we have each electron for 1 10 atoms. But why is it sitting on the Fermi level? That's not what explained. That's not what I know. Because that's the big question which I have asked already before several times. What is the connection between atomic orbitals and energy bands? And if I knew this connection, then I would know that if I have one electron on this orbital, then it will be on this band. But not that. That's what I not know. Okay, let me write it here. Maybe that's a complicated question which doesn't have general answer, but okay. And okay, there is a very unclear statement which I of course can't comment much. It's written that band on the Fermi level, which we have seen, actually, yeah, that's this one. So it's susceptible to a transition, and that transition is confirmed by the measurement. What is this transition? That's not what I know. Well, there is, of course, cited paper, but I can't comment much to which transition. Really, I have no idea. Nothing is given to me here to understand it. And that's not a rather important question. Don't see any consequences of this statement on anything else. And okay, I also can't comment next sentence that maybe that's this insulated band and we need a spin orbit and some reconstruction. So this is the reconstruction when the lattice distortion is introduced, and the spin orbit is also required, but we don't know what the spin orbit is. But together they create maybe this band. That's how I understand it. Yeah, and okay, that's already the question that I wrote some minutes ago, that in 7a we have a different plot, and before we are told that this is the plot that that is the truth one, but here Rossnagel writes that that's the plot that they obtained, and that's the difference. But what is the right plot, you may ask? Okay. Okay, I'm trying to extract some useful information from this sentence. Favorable electronic structure of the commensurate charge density wave phase. So that's the sentence which has no value because, of course, as we said, that there is a condition of energy, and if the energy of this state is more favorable, then the transition will go to it. But that was we know before, so I don't think that there is an important statement here. Just a comment about the same thing that we know, and right now I don't see any value in this sentence. And okay, so I guess in the next sentence there is this idea of stabilization, and maybe stabilization means the energy. So like how much energetically it's more favorable to have a charge density wave state. And in this transition a gap appears, so maybe there is somewhere gap here, which is meant the Mott-Hubbard gap, and that's the transition that is meant here. But this contribution is little. I mean, it looks like a couple of useless sentences. This are just comments about this maybe one band that they have obtained it, and also some people also knew it, but no one cares about, because that's the contribution of this one line, this little gap is negligible to the energy of whole this system and this state. And that's how I understand it. Now, okay, we can see the comparison of experiments and simulation. So that's the simulation, that's the experiment that was already discussed. And we don't have a experimental plot of this type because that's already for a different material. So that's the undistorted band, that's the distorted band. Yes. And basically, what is important is that this plot is very similar to this plot, which is a really good sign of tight binding model. However, if we just fit, but maybe it's still like it has some value because maybe we're not only fitting, we are taking parameters of this model, then we take parameters of lattice distortion, which is obtained from another experiment, put them into one model, and this model gives us this predicted spectrum. So that's already a not easy activity to do. Yeah, and as usual, that's the Brillouin zone, Fermi surface before, Fermi surface after. So there is this very unusual form of the Fermi surface, and I don't know like about it, how we can think about it. What is the blurred region? I don't know. And this is the little Brillouin zone, as usual, of the reconstructed state. And here the statement about these bold lines, that they are along the previous band before this reconstruction. How calculated, it's not the thing that I know. Yeah, and what I don't understand is that what's going on here. Like we haven't seen anything here in ARPES. Maybe ARPES is not susceptible for these states above the Fermi surface, and maybe somehow else we can obtain them, but I don't know. And that's just the question here. Now we are told to look here on this image, which we have already done. And this formula that we have seen, the only formula about spectral weight, was used to obtain that plot. But of course it's approximated because we don't know how to calculate delta function, so we used approximation. Yeah, and that's what I said, that it's approximately a good explanation for the obtained measurements of ARPES. And here it's written that this plot here can't resolve spectral fine structure details. So maybe if we knew how to resolve them, then these features of the plot will be easier to see. But that's what I think is written there, that we don't see them, but they should be in the model, because as far as I remember, as I was discussing like 20 minutes ago, there should be them. I mean, they should be taken into account in the model, but it's written here that they can't be resolved in the experiment. And what is that shadow band dispersion exhibiting density wave periodicity? It's not what I know. Shadow bands. Yeah, there are a lot of them. These are all the shadow bands. Somehow they were detected, but for some reason Rossnagel is not showing us this image. It shows the image where, as far as I see, they are not detected. That plot 11, which we have just looked at. What's going on next? Yeah, that's what we have went through. That's what we have went through. MK direction. So maybe it's meant about somewhere gap here. That's MK direction. But here in experiment, we, as you saw, there is just emptiness. But actually there are some shadow bands which have so little spectral weight. It's very strange why they don't have spectral weight. Here they do have, here they don't have. Okay. Strong spectral weight suppression in the Fermi surface map near brilliant zone boundary. Figure 11b. Maybe it's meant here, so maybe it's meant that here this is the brilliant zone boundary and we don't have any spectral weight here. So maybe this coincides with experiment, and that's what's written here. That's how I can guess what's meant. But I don't know why do we need to, like, what do we mean by reproduction fit? I guess that we have data from experiment of a similar plot and we compare it and we see this. So in experiments, there should be something like this in the commensurate condensed wave state. Okay, here we are told again that basically everything is fine and we have a good reproduction of the effects, and also told that some advanced effects like electron localization for the emission matrix element effects. I don't know what is meant by it, but it's written that it's not needed. So maybe there were some advanced ideas to improve the Taylor models, and I have no idea how to do it, but they were there, and it turned out that we don't need them, and reproduction is good even with this model. And that's this paragraph that we have went through. Okay, now maybe that's important statement. This ChatGPT told me that that's important statement. Let me read it again first of all. Next. So that's again requires a good preparation to the article, which I don't have, but the idea is that here we have a gap between and also in calculated model between two bands, and you can say that, oh, that's the Chernetsky wave gap. Actually, no, and the real Chernetsky wave gap is maybe this one. And if you know how this plot is consistent with this plot, mk direction, that's m, that k, so along this direction, somewhere there is the gap. So I don't know how they are consistent one with another. But we have written that that's not the gap, even though if you know how to transfer this image to this image, you will get from this red arrow, this red arrow. So maybe this error can be used for calculation susceptibility. And if we calculate susceptibility, we can get a change of phonon frequency. And also that's kind of modulation of the two-dimensional lattice. But I'm not sure about all of it. And that's my idea is that the main statement is that this is the gap and not this the gap of this sentence. Significant Fermi surface nesting may be expected. So it maybe means that if we have Chernetsky wave, someone somehow can expect that there will be even more elliptical Fermi surfaces, but that's not the case. But I don't know how to expect more elliptical Fermi surface, so I missed this argument, so I can't tell you more. And that's what I've already explained it, that true, it's between submanifolds. Yeah, okay, I know the answer to this question already. So what is the subtabilization of Chern density wave of the low-lying three-band submanifolds? That's not what I know, but maybe they give the biggest contribution to, okay, maybe not the biggest, but big contribution to the total energy, and this total energy becomes lower than and then what is that was a normal state, that's why we have this state, and that's maybe the stabilization. Yeah, here this stabilization, and it's written that these three bands give a contribution to it, and not these ones. However, it's strange because we have this spectral weight on them, so I don't know. And also, I'm not sure what is the stabilization. It's just my version of what is it. What does it mean to density of state increase at Fermi level? Maybe it's meant this peak. Yeah. And by the way, do I understand correctly that the area should be the same? Let's write this question. Okay, that's another question which I can think about it. I guess it's the same, but I didn't check. I didn't ask anyone yet. And okay, yeah, here there is the statement which I don't know how to calculate, but if you calculate the number of states per energy for all of the bands, maybe we need to just integrate all of this and all of this and compare both of them. I mean, for the bold line, for less bold line, then we should get this energy, which is lower for this gray area. But it's also written that, yeah, I mean, that's all what's written, but I just don't know where the energy is going. So maybe if we do this phase transition, we need to have a like reservoir that takes energy, or there will be some dynamical effects. That's the question that I wrote. And right now we are going to the second out of 3 material. It should be faster because basically everything will be the same as for the first one. Okay, maybe not the same, but similar. Here it's the, I guess, first principle calculations. These are the bands when we have a shrinking of a Brillouin zone, then shrinking plus lattice distortion. So all of it was inputted to the this magical tight binding model, and that's how this magical model gave us these plots. Note also that there are different directions. It's ALH direction, not gamma MK. Why we are also moving to another direction, it's not what I know. Okay, let me write this question again. Maybe I have written it already, but I forgot it already. Okay. I will try to answer it later, but we can neglect this feature and just see the similar results, but for different material, because we input different strange parameters which correspond exactly to this material and exactly this phase, and we're not told about these parameters, so I can't comment too much. The similar plot as was in the previous paragraph is given for the second material. And I don't know what is the reason why we have a different absolutely everything. This normal state has different Fermi surface. Condensed wave has also different Fermi surface. Maybe that's a very complicated question, and of course we need to read cited papers to understand it. But now let's just also notice that here we have this red Brillouin zone, and before we didn't have a red Brillouin zone. And so it's written that small Brillouin zone emphasizes the near match with normal state Fermi surface. So maybe it's meant that this Fermi surface is approximately the Brillouin zone, so it's nearly along the borders of the Brillouin zone. That's what's written here. Around this point, and remember these names of points, so K is that point, or H, because H is on top of K. Why is it important? I have no idea, but here there will be something about it written. Now again, to do this input, we need to know from somewhere the change of the titanium atom in the Condensed wave state, so we know it from some experiment. Yeah, so if atoms are not changed so much, then overlap of electron orbitals is not changed much, so electron structure should not change much. That's the idea here. It's written that it does not collapse to submanifolds. If we look here, yes, like if we compare it to this, then it does less collapse to submanifolds. But it still collapses to submanifolds. Here it's written that it does not collapse, but Yeah, but that's maybe just his way how to describe what we all see on the image, so maybe it's not an important statement. Semblance to the original. Yes, and it was written that here what we see is a little bit similar to what we have in the normal phase, and here this thing is approximately as this thing. This thing is not actually here, but it's like this thing. That's what is meant by this statement, this sentence. And there is a description of this. New gamma A points. So by this centering, where is written? So pockets on the new gamma A points of pockets of Fermi surface. That's just a way how to describe that image that you have just seen. So nothing is special here. Figure 9 and 12. Yes, and that's again the question about consistency of this, and that's what I'm not prepared to discuss, because maybe it's possible to see that figure 12 from figure 9, but for me it's not possible, so that's just a question for me later. No, and the second point is also the same thing, and it's the same question about how they are consistent, but okay, that's what happens after their calculations. And that's actually the image from ARPES results, or exactly this one, so we can compare them. Does it look the same? Well, approximately yes, but not really, because here we have a big line, here we don't have this big line. Yeah, but okay. Remarkably well agrees. If you can call it remarkably well, then call it remarkably well. I would say to some extent they agree. And we have the last paragraph about titanium diselenite. Let's read it. I'm just also a little bit, yeah, I'm just a little bit confused. So, okay, maybe I should correct myself that here, maybe that's not the 1/3. Here we are told that the modulation is square root of 13 times square root of 13. And how I have already reached this point where I looked at the calculation of it, but I'm not ready to reproduce it. So here it should be not the 1/3. It should be that we calculate area of one little Boolean zone, an area of a big one, and then we divide, and we should get maybe 1/13. Or maybe, yes, 1/13. Yes, and if we look at the change of each side, then it's a square root of 13. But that's like a geometrical thing, so maybe later we'll comment more about it. It's not a hard question, it's just the question that I didn't do myself yet. I just looked and then I went further, because there are a lot of other questions. So let's come back to this. So here we have 3 times 3. So here this argument is fully working, that we should have, like, I guess, 9 of these middle Brillouin zones to fit to get this big Brillouin zone. I will double check it later. And that, remember that there was this comment about consistence of, by the way, if we look here, and if we look here, Okay, why? That's the question that you didn't look at. But this thing is very much not like this thing, right? So maybe that's a problem. Why? 7 that's a good question. They say that that's a great model, but we see that this side is very different to this side. We don't have such sharp images like Fermi surfaces here. So it sounds like this is not really well applicable, right? But in this region, it's a little bit more similar. I don't know. That's just a question for later thinking. I'm trying to extract something useful from this sentence. So yes, of course, as we saw, there is this hexagon and Fermi surface is closed, but what is tempting to? It's not clear what is meant to do. That's the question again. I mean, which I wrote when I was reading it first time. So yes, there is coincidence, but associate occurrence of density wave with that Fermi surface is something which is, I don't know how to explain. Some strange idea is here presented. It's presented here. Let me again read it. Unfortunately, I forgot what happens here because maybe I understand too little about it. So that's just a link to the section 2 where we had a coincidence, full coincidence between brilliant zone and Fermi surface. Here we have a similar coincidence, and that's why maybe we don't have a Fermi surface after this change, because gaps are exactly created where there is the Fermi surface, so that pocket fully disappears. So it's not here anymore. I'm showing you experiment. An experiment is not that, see, we don't see that it disappears. I mean, it wasn't a big one, it became less one, but in calculations that that's the case. So some deep understanding of this perilous instability is required to understand this idea that actually maybe we can find some part of the Brillouin zone where Fermi surface is nearly the same as the new Brillouin zone, and this region of the Brillouin zone can give the biggest contribution. Okay. That's just my interpretation of that model that was shortly introduced before. And then again, if you follow this analogy, you can get this statement which I said, but it's not clear what is meant here. It's like analogy of one-dimensional case for two-dimensional case, but you need to work out these formulas at least once or two times for different particular cases in order to understand this attempt. And yeah, like I remember that there was a gap in density of states as in the figure 8, but also in the figure 9, because they're similar but for different materials. And it's written as a consequence of disappearance of that Fermi surface on that side. But why is it connected to appearance of the gap? It's not clear. That's why I can't comment you again. I don't know, is it written that that's just way to explain it, or they did the calculations and from the calculations they do these statements? But okay, here it's written that for some reason, even if it worked, then they calculated the energy, and the energy will be not from the Fermi surface. And we have another statement that if we use this density of state to calculate energy, and if we could use some special experiment to calculate also energy per atom, then they will be in a okayish experiment, coincidence, like in okayish agreement. But that's not related to this. I don't see how it is related. This is not related to this, and that's a strange idea. That's the summary of this paragraph. So maybe it means that one interpretation of this result is not quite good because it implies some calculation of the total energy, and total energy is calculated approximately fine and is calculated from other electronic states. So that's why one can't think the way how it's proposed, how he could think, but it's basically a useless paragraph. Okay, the third out of three and the final material for today's stream is titanium diselenite, and unfortunately that's the biggest material and the last clear one. Evolution of band structure is shown here, so we have a little bit different plot comparing to figure 9. We don't have a density of state here. We have more different changes. So reconstructed band structures here as usual. Now there is the inclusion of bond strengths with last is distortion part, and as usual, right? Zero distortion amplitude as usual. So yes, that's for observed distortion amplitude. That's for twice observed distortion amplitude. And why do we need the twice observed? Maybe it should be definitely explained below. And we will also be told names of this band. So I guess this is 4P, this is the 3D band, so this gap occurs. And we will compare this actually with this. But here already we have some measurement and the energy is higher than Fermi, so maybe I need to learn ARPES better because here we didn't have them. Here we clearly do have them. And I guess that's about comparison of this plot with this plot, but we will see also some special figure for this section. Let me just check how much is left. It's left half of page, 1 page, 2 pages, 3 pages are left. Okay, let's try to do as maximum as possible. Okay, now we have a larger displacement of okay, now we have the displacement which is in the middle of two materials. Some electronic states are confined in a small volume, so I guess that's about the decreasement of the Brillouin zone, so it's still there, but it's not as big as no. No, yeah, but it's 2x2. Yeah, it's 2x2 reconstruction, so it's not, the change is not as big as for the previous material. But it can't right now from top of my head compare square root of 13 to this, somewhere close to the first material. Okay, maybe it's written that indeed, like, it's the change of Boolean zone is smaller than the bigger change is bigger, and final unit cell is the smallest. Okay, that's what's written here. And it's related to the number of upclamp bands, which is lower. So here we indeed see that there are less bands, but I don't know the connection between this shrinking of the Boolean zone and number of bands. And that's a question of general understanding of condensed matter. And I don't have this preparation yet. But we see that here, I mean, it's stated here that this lattice distortion is not influences the band as big as it was expected. It could be expected. Why? I don't know. It's not explained, but further, maybe it will be explained. And okay, let's look at this undistorted phase, which we have just seen. That's this image, but another. Okay, let me use my app for fast displaying of some parts of PDFs. So you see, we don't like to scroll, so that's why we do like this, and like this, and like this, and that's how we can look at 2 pages. Okay. Okay, so we have 3 bands here along the, I mean, around the gamma point. 1 band, 2 band, and 3 band, and that's another 1 band. That's the selenide band, and these are the titanium bands. Why they are so, that's the question that goes beyond this article, so let's not discuss it. And that's, I guess, obtained from the calculation, not from experiment, so there is no spin orbit coupling. And it's not written here how important spin orbit coupling is, but maybe something important, something is also left, which should be taken into account, but I don't know how to do it. And what is the indirect band gap is set to 0? And maybe it means this one, so they were tuning these parameters state by the model to give this shape without the gap, because this will coincide to some measurements before. That's how I guess what happens here. Now we have a degeneration because we have this folding. Somehow it gives us this picture. Why it's exactly, yeah, how much? 3-fold degenerate. I don't know, but yeah, some advanced intuition should be here, maybe I will later speak with ChatGPT or some people who know this article, and they will explain me how to connect this folding to the number of degeneration. Right now, we're given the statement that that's what happens from this plot if we do shrinking of the Brillouin zone. And the generations are lifted along the gamma direction. So I don't understand the sentence. That's, I guess, just explanation of this plot. So in this plot, we have more bands. They are here, here, and somehow they are degenerate. So that's also a strange thing that here we have a big spectral weight, here we have less big spectral weight. So how does it happen that one bold band becomes not bold? That's of course not written, but okay, we can just guess and just go further and believe this strange state binding calculation. Yeah, and the gap remains 0. So basically that's just description of this plot, which maybe is not important to understand, because anyway we can't understand it without doing these state binding calculations. And maybe here finally we will see something useful. Let's see. And that's the introduction to what I was telling before, that for some reason they decided to increase this amplitude of the change of the lattice, and if we have this new distortion amplitude, then we finally see a gap. Maybe later we will see why we really need the gap, because before there were no some experiments that really requires to have the gap. Maybe later they will be. So yeah, that's what I have just discussed. Maybe here there will be something more useful. Okay, I was too lazy to open figure 7c, but okay, let's just move and open figure 7c. Maybe this will give us some insights. And I forgot the names of the figures. Maybe that was the figure 7c. And I was trying to understand last stream, is it from experiments or from theory? Most likely from experiments. So yes, this was proposing some time ago that we should believe that this is exactly what's here. Of course, I don't see it. It's not explained much, but okay, at this point, when we read that sentence, we need to believe that this plot is exactly something here. M is here point, gamma is here. So no, fortunately, it's not explained how we should understand this plot, so it's impossible to compare them. But this sentence tells us that we should believe this, because it's written in good agreement. But okay, we have the next plot, which will maybe give us something finally really understandable. Okay, spectral weight distribution. What it means? Maybe it means that that very advanced state binding model that what was just described, but we don't see a formula for it, but still it's there, so it gives us some bands. So we just believe these clever people who did these calculations. And on this plot, we see the spectral weight. So these black lines, they mean how probable it's for electron to be on this band. That's how I understand spectral weight. And I was discussing with ChatGPT what is the spectral weight before the stream. So that's maybe a good explanation, but maybe it's a bad explanation. Anyway, spectral weight was present throughout the stream, and here they may be continuing doing these calculations. Let's just again look at these plots and try to understand what is the meaning of it comparing to this plot. Maybe gamma m, maybe this is something like this. And I should confess that I wasn't thinking much about this plot. Let's see, around gamma point and around m point. So yeah, that's maybe around the gamma point. So that's exactly a close look to, this is the close look to this plot. This is the close look to this plot. I'm pretty sure that that's the correct interpretation. And so here the displacement written is 0. Maybe it's about the calculation. So maybe that's plot. This plot is maybe this plot, because here we are told that there is no displacement of the like titanium atom, which is the central one in that like lattice distortion. And here there is the case where I guess we have this twice displacement. Yeah, exactly, twice experimentally observed value. Okay, so that's another version of these plots. Now we understand it. There is this also strange black line which originates maybe from this black line, but okay. Doppler spectral void. Yeah, and the last thing that I should tell you, okay, I don't know what are these epsilons. I didn't write question yet, but it's, I guess, that's this distortion amplitude that's written here. So that's this epsilon, that's 0. Okay, that's clear. I guess these are the top bands, which are not just important. I mean, they're not important. That's why there are, okay, there are comments. Okay, there are no comments about them, but let's just not focus on this. The last thing that I wanted to comment based on this sentence is that here is the spectral weight. So if we take, yeah, that's the sediment band, so it has a big spectral weight, and this is the conducting titanium band that has low spectral weight. That's the usefulness of these images. And now we go further and we need to read this, and let's check how much is left. Half of a page, 1 page, and half of a page. So 2 pages before we finish. And I'm not sure about my time because I need to finish as soon as possible, but I need to do the high quality discussion also. So yeah, okay, let's just try to maybe speed up. Okay, that was discussed here. Okay, let's do this. Yeah, I have no idea how did they decide to increase twice the distortion amplitude. It looks like guessing. It looks like maybe it's not a good argument for comparison with experiments. Looks very suspicious, but that's what we are told, at least. Figure. Okay, that's the figure 13 that we have discussed already. And okay, I was announcing that this figure gives us something useful on this, I mean, explains something on this figure. As we see, the scales are different, so now I can't comment much about it. But okay, we just need to believe based on this sentence that the agreement is good. Okay, that's what I was thinking before the stream about some flattening of a band, and maybe it's better not to comment this because I can't really understand it. Just don't want to miss any important information, so I don't really want to skip sentences. Okay, let's pretend that explanation is the following, that there was some band here and it became like this. So maybe, okay, maybe this is the selenide band, so it becomes more flatter, slightly. It's nearly invisible, but okay, that's the best thing I can tell you about this sentence. Looks like a very useless sentence. Symmetry point. Okay, that's related to some folded valence bands. Oh, okay, let's just imagine that there is no such sentence. It's very unclear. They imagine, I mean, related to some phenomena that you don't see in the plot, and they explain it by folded valence bands and some maximum of Fermi energy. And we have cited paper, so I mean, it's just reference to this paper, so there should be a better explanation, but okay, for reading of this article, it's better to just forget these extra comments about the changed bands. Yeah, now they suddenly do this discussion of twice distorted amplitude. And okay, I don't know what to tell about, because see, they just do it. They don't explain why. Does it make sense? Of course, no, but they do. And then they, at some point, maybe they will say that it's a good comparison with experiment. But okay, let's just read. And okay, then they cite again the same paper and say that that atomic displacement is too small to maybe reproduce the observed Bain structure. That's what is meant here. So I don't want to guess what is the connection between two sentences, so looks like not so important sentences. But we have the next paragraph, which is here. And based on the first sentence, we already know that nothing will be useful in this paragraph, because that's already more than 10 hours how I stream Rossnagel's paper, and I already know that no, he just tricks us by proposing to explain Chord density wave mechanism, but he doesn't explain it. So another attempt, like 10th or 20th attempt, is presented here. And we have a very bad statement that it confirms something, but we don't know what, because we have this cited paper. That's the only thing that we are given to explain it. Okay, now we have again this link to the lowering of the valence band and lowering of the total energy. Okay, we were not told about the lowering of total energy, but now we know that it lowers total energy. But now we have also splitting of two bands. Okay, we need to imagine some plot like this, so somewhere splitting. Okay, there is some splitting somewhere. Okay, so we know already. And they say that it originates from spin orbit interaction, but in tight binding model, maybe spin orbit also was used, but maybe they were calculating it numerically. So that's just a comment about obtaining of this splitting. And again, the sentence, which I can't explain you immediately, so I need to think more about what this meant. There are also fluctuations. And okay, and from fluctuations. Contribution observed p-band split in unit room temperature. So like I have read right now 3 times this sentence and I don't understand what is the meaning of it. Okay, so if we have room temperature, then there is still some electrons that maybe tend to form charge density wave, and it doesn't contribute to p-band splitting. Maybe p-band is this one. Aha, that's written maybe here. Titanium 3D, yeah, and selenite 4p, so maybe for this splitting. So, okay, maybe by charge density wave we mean that there are some also fluctuations and they are not giving us the splitting which was somewhere observed for this material, but we don't have this plot, we just have this citation. Where is it? Maybe this one. I don't know actually which citation is meant here. But as I told you initially, I wasn't remembering this paragraph, but based on the first line, I have predicted exactly the right thing, that that's a useless paragraph. I can't even summarize you what it gives. Maybe that's the lack of my basic preparation, but I really try to understand what happens here, and the conclusion is that there are advanced useless comments about the plots that have already been presented. Okay, we have 2 more paragraphs and then summary, so I think I will fit into my time. And I guess that this will be a similar paragraph, because now we have attempt to describe origin of this state in this material. Let's look at the comments about this origin, but it's also not clear that, like, what is the question about the origin? It's like again attempt throughout of this article to give us some working model, but we don't have any real attempt. We have just words tight binding model. And like, how can we understand tight binding model based on citations? You need to write explicitly which model is used, and then we can understand it. But of course, there are cited papers. I could look there. It would just take way more time, and I don't know. I'm not sure that it would pay off. So let's read this sentence. Tradition appears to be small. To drive the transition. Okay, we have a statement which, of course, it's very hard to understand, because what is the driving of transition? Of course, we have discussed it already before, that there was this story. Let's do it carefully a little bit. There was this story of these whole formulas which are discussed on the second stream, as far as I remember. And here we've written that some changes of the electronic energies are sufficient to derive the transition. And that's another story. So I guess he means that it could be a different approach for drive the transition. So there could be a different approach for this transition, and some states near Fermi surface can have a big contribution. Or maybe no, that's what I guess it's meant by this question. And the motivation that K-space volume is involved, I have no idea. Maybe it's about the shrinking of the Brillouin zone, which we have seen a lot of times today, but the statement's unclear clearly. Okay, and to answer this unclear question, we can find the energy gain, which we need to believe to, because there was some calculated density of state, and and then we need to believe that that's the energy gain. okay, have shown you some numbers for the previous material, but for this third material, this number is here. Compound is okay. That's just the statement that's again. I mean, that's a similar end of this discussion as for the previous material. That's the energy gain. It's approximately the same as an experiment, but it's actually not the same as an experiment. So one can ask a question which maybe will be unanswered for decades. Why is it so? What is the difference? Of course, I have no idea, but at least it's a good thing to check once this paper. But maybe previously it was written that this energy, the states near Fermi energy, are not responsible for the phase transition. But here for this material, it's maybe possible. Appears to be possible. Maybe it means possible. What is meant by stabilization? It's not the thing that I know. It was discussed, but I didn't select these formulas into my list of key formulas because it was rather abstract discussion, but I guess they mean that there is another mechanism for the stabilization, and it's meant here that it can work for this material. Okay, but I mean, that's like useless statement, right? It gives us nothing really useful to work with later to describe something more or to use this material somewhere. Okay, now we need to remember my maybe third stream about the excitonic insulators. In scope of this article, it was written that that model is applicable for this material, and now we are asked about this contribution. We were not explained what is the excitonic insulator model means, what does it mean, but okay, there is a proposal about several sentences to discuss this connection between that model and the state binding results. And this strange, unknown, unexplained state binding results suggest that there is this excitonic contribution. Of course, no explanations are provided, but let's read the last sentence. Produced by the present. Yeah, okay, and here, okay, nothing is explained here. It's just the citations of 3 papers, and how these results suggest this excitonic contribution is not clear. Of course, I'm not able to answer this question. And the last statement was the one that we have already did, that results that they presented are approximately similar to the measured results. So again, this is the measured results. These are the calculated results. So if we look on this thing and on this thing, we need to believe them that that's the same. That's the main conclusion here. And just I want to read my comment about it. I am just I'm just highlighting that that's the conclusion, but that's like really strange thing that you can't just twice increase the amplitude. What if you fit just like increasement of amplitude 1.5 times, or like any time that you want, and try to fit other models? Maybe they would not work, but there is no argument for this to work at all. So, but okay, that's what we're given. But when I think about it more, it just makes no sense. You can't introduce twice bigger distortion amplitude as measured and say that that's a good explanation. Okay, no argument is provided here to support this claim. And finally, we have last half of pages before the end of the stream, and that's the summary. So it should be the easy part. Yeah, so we see many changes in electronic bands, and there are some ideas behind it. That's my summary of the summary, but let's read it more carefully to check if I didn't miss something. Yes, all of this was in the focus of several studies. We already know figure 7 with some results. That's actually the figure 7. They do the tight binding models. Some key features can be reproduced. Which exactly key features? It's very hard to say exactly. I mean, we have discussed it, right? This thing is like this thing, but yeah, okay, maybe I should just add the comment here and not the question. Because approximately already understand it. And let's read what's next. And that's already written here, that they're reproduced. They're also reproduced, nothing is important. I'm too lazy, but I need to push myself and read these 4 sentences, because right now it's not clear. I need to read again what's meant here. But by the way, as far as I remember from my preparation, there was an important statement which was not explained well in the article. So if we do this tight binding calculation, we get this change of spectra. And I highlighted it during my discussion, but okay, I'm not sure how important it is, but that's like the real and density wave gap, not this gap. Okay, and they say that this density wave gap is large. What is the value of this thing and why is it meant to be large? I don't know. Like, that's the density wave. That's what we were told during the article. It's written that this gap is large. I mean, that's for one component of the 3, but for others, I mean, for second one, we have also similar plot. For the third one, we're not given the plot, but we can guess that it should be somehow similar to this one. So maybe that's the large gap, and that's what's highlighted here. And what is the K dependent? Oh, I have no idea. Maybe it means that here it's slightly changed, but it's written strongly K dependent, so I can only guess. Yeah, and that's what maybe we're told before, and that's the summary of it. So subbands appear, and of course some mathematics is assumed, which I don't know. So maybe one day I will do these calculations and get these subbands and then gaps between subbands. And here it's highlighted that there are the subbands and gaps between them. And structure change. Yeah, and that's what also we were told in the theory, that it's connected to the displacement of atoms, because they introduce different parameters of the model, and with different parameters we will have already gaps. But everything is covered with the words tight binding model, so we need to read cited papers to understand why is it exactly so. But that's the important message of this part of the article. Yeah, and this Fermi surface nesting, the problem was that it's not explained how it can be used. It's just the idea was sketched, and here it's written that they just do tight binding approach and don't touch this strange idea, which was not very explained. And here they emphasize that it's not important to use this idea here in these calculations of energy bands. So basically, the whole chapter 2.1, I mean, whole chapter 2 seems like a very useless one, because anyway, to do some predictions, we need some measurements. And when we do some measurements, for example, of lattice distortion, then we can use tight binding models, and we don't need all of this abstract theory, because anyway, it's not clear how to use it and to which materials we can apply it, to which we cannot. And in scope of this theory, if we generalize it for two-dimensional models, we have the Fermi surface nesting idea, but here it's written that we are not using it at all to get the main results in the article. Okay, finally we did the summary, and let's just summarize everything what we have passed through. And today, during the stream, we have discussed all what I'm scrolling through. No, we didn't discuss this. We have started from here. So we were told that that's the name of the model. We were told that these are advanced parameters there, and that was the results for the first material. There were advanced discussion of how this model was used, and it's very important that they were calculating spectral weight, and that's the idea and the formula for spectral weight. Of course, it's very hard to reproduce it. Okay, maybe ChatGPT can help right now if he has a lot of articles in his database on which he was taught. Yeah. Maybe he can help and use this formula to get some plots, but that's the abstract formulas. And this discussion, the first material, we have just seen the plot for it, and that's the second important plot for it, and that's the band structure of the tight binding models. These are the Fermi surfaces of the Brillouin zone before and after, and a lot of advanced comments. I mean, some advanced comments are present about it. Nothing of them are really important. And I have discussed recently some of them. And that's the result for second material. That's the band gap. And that's the spectral weight. And that's the change of the Fermi surface. Again, some extra comments, which I don't really remember right now on top of my head, but I don't feel that something really important was there. Just description and comments about different ideas. And that's the third plot for the third material. And we are told that all of this is consistent with, to some extent, with this thing that I'm showing you at the left. And that's the experimental results that were presented before. That's just a close look of the plots. And some extra comments which do not really give big value. Okay, so that's the stream. I did what I planned. That's very good. I'm a little bit late to my next activity in my life, but I hope that someone will write some comments and someone will join the stream, or someone will save their 20 hours of thinking about this article if they would want to understand this article. That's the only advantage that I imagine from the streams to the viewers. But I'm really happy that at least one viewer joined today. Thank you. Okay, bye-bye. See you next time.